Guys, it's interesting that if I had to teach you time series analysis reading 6 as a standalone, I think everybody would leave straight away. I hope you don't leave anyway, okay? But coming after reading 4, which is simple regression, and in particular reading 5, which was multiple regression, with all of the issues that come with multiple regression, particularly, guys, we're going to see what relates to this particular session. This is really, reading 6 is really just an addendum, in a sense, to those 2 readings. Okay, there's not going to be a whole, I mean, you'll see, even if I gave you a question to start off now, you would have, and it's a question specifically related to time series, you would probably still be able to do quite a bit of it, knowing what you know already on the other regression methodologies. So I hope I don't bore anyone to tears tonight. Okay, just in terms of what we've still got to cover, guys, we've done reading 4, simple regression, reading 5, multiple regression, reading 6, we're going to do tonight is time series. And then next week, okay, we're going to knock off, it's interesting, we're going to do the whole of study session 3 next week, which is 3 readings. They're gentler, I don't know if they're gentler readings or much more theoretical readings. We do machine learning as our 1, which will be reading 7. Then we do a little bit of AI and that kind of stuff, big data, Mark, which is reading 8, and then reading 9 is like algorithms. It's all the new stuff that they've thrown in, networks, k-nearest neighbor, all those kind of neural networks, deep learning, quite theoretical stuff, but very important, obviously, guys, in terms of, but we will do that next week. Okay, guys, so tonight's class shouldn't be that long, okay? If anyone's planning a date, I don't know, is Thursday night still the night or not? In my yard, my day, it used to be the night. Yeah. Yeah. And guys, I don't know if you caught it, I'm sure you did. Vern, I got that article sent to me a little bit before you posted it, but thank you for sending it, notwithstanding. And the Chinese guys are, first of all, they seem to be getting better pass rates than us all, number 1. I don't know if that's true or not. I didn't take that out of the article because you can never really tell, to be honest, because they're not published or anything like that. No one really knows. But what was quite interesting, and I had one of I taught the Kai guys on Tuesday night, the Kai level 2 guys, and one girl picks up a hand and says, because they do the same ethics as you guys do, exactly carbon copy, and they want to know if there's an easier way of studying it. I don't know if like a hack or I don't know what they call it. And the truth is, guys, whether you like the Chinese or not, whether you think they're messing up the curve or not for us or not, whatever, is what it is. They're there. We've got to work with them. Okay. But that work ethic, guys, that's what's, and the one guy like laughed and he said, like, 300 hours, that's not even like a commitment in their book. The amount of hard work that they often put in to get to where they need to for their exams and they're getting into varsities and that kind of stuff. 300 hours, he said he would give much more than that to get the CFA. And guys, that is that's just maddening commitment. And, and it's just time, guys. Not just time, because time is the king. Okay, but that's what it is. I'm still going to rebrand, guys, at some point when I get more energy, more time. Okay, but obviously actual work comes before my rebranding, but I'm going to rebrand 400hours.com. So we get rid of that notion of 300 hours. 300 hours is gone. The Chinese have killed that for us, by the way. You can blame them for that a little bit if you like, shifting the curve a little bit. And I think it's a good thing. When I blame them, we can, but yeah, that might be a nice marketing. But guys, we've got to be looking at 400 hours. Okay, and that's I think it's going to get you through is more time, more consistency, and just more questions and applications. And you saw that from it's a lovely article. If you haven't read it, the one that Vernon sent, please just do take a few minutes. I took it as inspiration more than as anything else. Just have a read of it. It's a nice one, particularly coming into December. And I try to make a meeting with somebody next week Thursday, and. No, they can't make it now. I said, well, why not? No, they're going on holiday the day before that, the Wednesday night. I said, but that's like the 2nd or 3rd of December. They said, yeah, it's December. And a prominent business, but I'm not going to give you names, but a prominent business person. So I said, not a problem. we can, you know, and he needs me more than I need him, by the way. So I said, okay, well, you'll call me when you're back. When you're back, you're going on the 2nd of December. When? Mid-December you're back? Late December? 17th of Jan. I said, but now I'm stuttering. I said, that's 6 weeks. He said, yeah, in the Cape. I said, wherever it is, it's a long time. I said, but anyway, so I'm not knocking him, and if you can afford 6 weeks, you know, take it. But obviously, I know what you guys have got coming in June 2020. You know what you guys have got coming. Make use of the time. And I'm definitely not saying don't take a break. You need a break. And you'd be crazy, guys, if in the end of this year, after a tough year, we've all had a tough year, I'm sure, take a break. Take 2 weeks, but don't take 6. Okay, 6, you can get bed bugs like that. I don't know what he does for 6 weeks, but each to their own. But do use the time wisely. Particularly if you do have to be in the office and it's quiet, pull out your files. You know, so just as best one can. Just that application, it'll get you very, very ready for the new year. Okay, guys, let's jump into time series, and it's not too crazy reading. There's a few little concepts that we've got to get through, but in general, it's not too bad. And guys, a basic intro to time series is what we've seen already. Previously, everything was dependent on an independent variable, which was my X variable. When I moved to reading 5, which was multiple regression, wow, then I had 2 or 3 or 4 independent variables, and that drove what? That drove my Y, which was my dependent variable. What drives everything we're going to do tonight? Time. We look at 2 major time models, guys. We look at the one kind of a time model that says that the results will be dependent on what time I want. So let's say, for example, there'll be a different result in time period 1 than there'll be in time period 300, for example. Okay, as time moves on, what would have changed? Perhaps inflation, perhaps price movement, something like that. Another one I look at, guys, we also saw it last week, by the way, which is where the results are dependent on last week's results, the week before that results, the week before those results. We'll look at those 2 kinds of models. Typically, those are called AR or autoregressive models. They just, and guys, it's such a fancy word. We're going to look at some nice words tonight. Co-integration. Wow. And all these kind of things, the unit root and all these fancy terms, don't let the words get to you. Let's get a big understanding of the big picture, and we're going to move on from there. Guys, let's jump in. Let's start. Okay. We start off, guys. Okay. And I start off over here with a linear trend model. What's a linear trend model, guys? Okay. It's a straight line, hence the word linear, isn't it? Okay, so a linear trend model. Have you seen this one before? Am I boring you to tears? We've seen this a zillion times before, haven't we? Nothing new over there. Okay. What changes over here a little bit, guys? Okay. We say Y, that's my dependent variable, what I'm trying to predict. Okay. And I'm going to just take, if you go down there, we've seen this all before. The Y with the hat on is the Y that is there to predict, is equal to, is the BO, which is the intercept, plus the B1, which is the slope at whatever time period you wish. You're happy with that? And why is it a linear model? Because it moves linearly. Okay. How would we know? You could just look at a, what's his name? You could just look at a scatter plot, couldn't you? And you could see quite clearly if it is linear, what would you see? You would probably see, it would look a little, your dots would look a little bit, say something like that. Am I right? Then you could see, oh, that looks quite like a linear, not a perfectly linear picture, but yet notwithstanding a nice linear picture. Then what would I use for my time series? A linear trend model. Nice and simple. And guys, let's look at a quick example over here. Okay, an analyst wishes to predict the future inflation rates. Step 1 is to estimate the linear trend in the rates. For this, we use monthly CPI data. Okay, the data runs from Jan 95 for a period of 228 months. What would be that? That's obviously, guys, that's my sample, isn't it? And would I be boring you if I say to you, those are my total observations? What degrees of freedom would I use, guys? when I'm looking for my degrees of freedom, because remember, I go and look this up on a t-table when I'm looking for my hypotheses. So 228 months, how many variables have I got? 2. So my degrees of freedom would be 226. You guys comfortable with that? Nice and simple. As I said, guys, a lot of the stuff is repetition. Okay, but nothing wrong with repetition as well. Okay, we look at my, let's look at some of the stuff that we pulled out from the ANOVA or the regression table. There's my B0. You happy with that? My coefficient. My B1 is over there. There's my standard error. How do we calculate standard error? Just very briefly, it is what? 1 over the root of t. Yeah, we've seen that many, many times before. Okay. And by the way, it's just purely a kindness and a time-saving thing for you guys, because remember, they don't have to give you the t-stats, do they? How would you calculate the t-stats? Remember, it'll just be your regression coefficient. You happy? 2.8853. You see where I got that from, guys? It's over there, divided by the standard error of 0.5754. That'll give you your t-stat, the same t-stat that's over there. Okay, that just saves you a bit of time, but I mean, you could calculate those quite quickly and easily to the extent that they don't give them to you. You guys comfortable with that? Again, nothing new. Okay. And of course, guys, you can see why the t-statistic on the trend coefficient B1, your slope is negative, because your coefficient is negative. So to get to my t-statistic of 0.86, I would go the minus over here, coefficient divided by the standard error over there. You guys comfortable with it? Nice and simple. Look at your R squared. Not a great R squared, is it? Not a convincing R squared. There's your standard error. There's your observations with a Durbin-Watson of 1.09. Okay. I'm not going to speak too much about Durbin-Watson just yet. You've seen Durbin-Watson there already before. We'll talk about him in much greater detail as we go. Okay. Good. Everyone comfortable with my data? Okay. So, and it says, do all your stuff, do all your work, guys, at a 5% level of significance. So away we go. We're looking up at the critical value. I go to my t-table, guys. Let me just quickly, just at 99% sure, guys, that they're going to give you the numbers. This is not what they're trying to test over here, but just in case, let's just pull one up for you very quickly. And please don't fight with me as to why they don't give you a, what's his name? Why there's no 226 exactly on the table. Okay, we know it's not going to be there. Let's have a quick look. Okay, I want to get like 100 and infinity, 200 and infinity. Let's go. So guys, there we go. So I'm working somewhere on my t-tail at 226, and that's why, guys, don't stress about the exact degrees of freedom. That's going to fit somewhere in between here, isn't it? Okay. And I wanted at what? I wanted at 5% level of significance. It's a two-tail test. I go there. I pull all the way down. Just keep going. Keep going, and it's 1.96-ish, something like that. You guys comfortable with that? Okay. I can't tell you exactly what it is, but it's somewhere over there on the table. Okay. Let's pop back to the notes. Okay. And I've written it out for you. We're looking up the critical value. We arrive at a value of 1.97 at around about 226 degrees of freedom. And what would you say? Since the t-stat, okay, and I'm only looking so far at the intercept, guys, which is 5.01, okay, is way in excess of the critical value. What would we say? That the intercept is statistically significant. You happy with that? So I could conclude here. I would give it a tick. Yeah, that one is statistically significant. What about the trend coefficient, or B1, or the slope? Okay, that is below the critical value, it's minus 0.86. You happy with that? So what would I say? That is not statistically significant. Okay, good. You guys comfortable? So I've tested my two variables, my two coefficients. One is statistically significant, one's not. What would I need to do at this point, by the way? We can carry on working with the example, but once you found one that one of them is not statistically significant, you should probably go back and try another equation, shouldn't you, to try and get that till you can make sure that, because at this point it's not going to be such an accurate predictor, is it? Because it is not statistically significant. Good. Over our page. You happy how we got to the estimated regression, guys? Anybody not see that one? Okay. And again, it's exactly what we've done up until now. What's the only thing that's changed when I draw up this regression equation? The only thing is that the t has been replaced. So the x, sorry, has been replaced with a t. That's all. To tell me what? That I'm in time series. That my whole regression is what? Is time-based, not whatever based. When we used x's, what do we use for x's? Hours studied, or whatever. Now I'm using time. That's all. Only difference. Okay, look over here. Assuming that we wanted to predict the inflation rate in month 240, what would I do? I run my exact equation. What do I put in for t? 240. That's it. And then I get to my predicted equation of 1.9733. The higher the percent, the higher the inflation rate. Because remember, if I had to try and predict the inflation rate at month 100, what would it be? Quite a bit lower, wouldn't it? What do you think? Or not? No, it's the other way around. Other way around. Yeah. So in this case, what would you conclude here? The relationship between time and inflation rates in this particular regression, there's a negative relationship. You happy with that? So it might still be linear, but it's not positively linear that way. So if you have to look at a picture, this would indicate what? A positive linear relationship. You happy with that? Could be going that way. But still linear, isn't it? Still linear. Linear just means a straight line, that's all. You happy with that? But Vern is right, that this here, because you can see the minus falls after the, if it wasn't a minus, okay, it would be a different picture, wouldn't it? If it was a plus, it would be the other way around, wouldn't it? And as the months go by, the inflation rate would be higher. That's all. But you can't really, and I don't want over-analysis over here, but guys, all I want you to remember is that the only difference over here in a time series, in a linear time series equation, is I've replaced my x variable. This is what? This is back to reading 4, isn't it? This is simple regression. There's only one multiple. What's that one multiple? What's the one variable? It's time. You happy with that? I've replaced my independent variable x with a t called time. Why? Because everything I'm working with now is what? Is time related. The longer out I go, the higher or the lower the inflation rate will be. The further out I go, the higher or lower the interest rate, or whatever it is, whatever I'm trying to test for. Does that make sense, guys? Okay, good. Log. So that was method 1. Where would I go for log linear? Remember, log. The minute there's log, what would you tell me? That it's no longer discrete at a point in time. It is continuous. The minute the time series data grows at a continuous rate, okay, over here, the minute is growing at a continuous rate, in other words, exponential growth, not just linear growth, okay, then I need to use logarithms. Okay. Good. Okay. Look at your equation. Very similar, guys, but except over here, because the growth is no longer linear, but it is exponential, I use this formula here. Well, tell me if you like it. It says yt, the predicted y, is equal to the exponent, because I'm in logarithms, of what? BO, which is the intercept, plus B1, which is slope, times time. So what's this? Exactly what you saw before, am I right? What's the difference between this one and another one? I'm just using logarithms, that's all. Nothing different. Why am I using logarithms? Because the growth rate is exponential or based on continuous growth as opposed to normal linear growth. It doesn't grow at a linear rate. It does this. It shoots all over the show. Okay. Let's have a look at an example, guys. Okay. By the way, so I just wanted to show you one thing more. Following a little bit of maths, and don't worry about the maths. Okay, if you like the maths, I've showed it to you over here. But at the end of the day, okay, your equation will come down to this. Okay, to get rid of that, what I do, the ln of y is equal to what we've seen all the time up until now. Okay, and I'm going to show you how to do all of that as we go. That's why don't worry too much about it, but guys, that's typically how you're going to see what your equation looks like. And then, so as soon as you see lns, logarithms, exponents, you know that the growth is exponential or continuous, and that's why I can't use a linear model anymore. Okay. An analyst wishes to predict future quarterly sales. He goes from January 1995. He's got 76 quarters, and there's your regression equation over there at the bottom of the page. Nothing's changed. Over our page. Okay. Same, nothing's changed over there, guys. Constant. Nothing too crazy over there. Okay. And what would and let's say, for example, he wants to predict sales for quarter 77. What would I do? Okay. Look, and just for this is a little bit tricky just in terms of the calc, but other than that, not too bad. You happy that I normally go my normal B0, 5.1304? You happy where I got that one from? That's the intercepts, nothing's changed. You happy with that? Plus, and you can see here, because my coefficient, my slope coefficient, in this case we call it a trend coefficient, is positive, so I go plus 0.0464. You happy? Times 77. You happy with that? Okay. Good. Okay. How do I, so if I stopped at this point and I just summed what I've got over there, guys, what would I have? 8.7032. You happy with that? But what's the real answer? It's ln is equal to 8.7032. How do I get that's not an answer? Not yet. How do I get it into the correct format that I'm looking at? So you go, okay, you put your if you go into your calculators, guys, 8.7032. Second function e. That gets rid of the ln, doesn't it? To get the ln onto that side and to get your answer, you take 8.7032. Type that in first. Second function ln button, which is in fact the e. So if I make sure that you get 6022. Haven't got it. And what would you conclude, guys? You would conclude that projected quarterly sales for the 77th quarter is 6022. Yeah. Okay. Everyone comes. So guys, if I had to stop at this point in time, what would you tell me? I've done two models only. I've done a linear model, a linear trend model, and a log linear a trend model. There we go. So there's your log linear, which is number 2. And if I take you back a page or 2, there's your linear trend. You happy with that, guys? When do I use linear? I use linear when there's a linear trend. When do I use log linear? When the trend is not linear anymore, but it is continuous, or that's your right word, guys. There we go. It's continuous. Okay. It grows at a it doesn't grow at a constant rate. It grows exponentially. Everyone comfortable? The question is on the bottom there, which model is best to use? Okay. First step, draw yourself a scatter plot of the data, which is what we spoke about a bit earlier. Okay. If the data points are equally distributed and you can see a nice a number of dots above the line and a nice number of dots below the line, what line am I talking about here, guys? The line of best fit. Okay, now I can see I'm boring you, but it's better that I bore you than You don't understand. Okay. But you can see, guys, there's a lot of repetition over here for things that we've seen thus far. Okay. If you can see an almost an equal proportion of dots above the line and below the line, then you can say, yes, this is quite linear. Then what would I use? I'd use a linear trend model, model number one. Okay. If it starts to look like a bit of a curved type of shape, but looking a little bit, things like that, there's exponential growth here and there. Okay. Then I would have to use a log linear model. Okay. And the more it starts to look a little bit funny like this, a bit of a upwards, downwards type of a shape like that, more curvy, what's that an indication of, guys? You know this, that indicates that there is this thing called what kind of a correlation? Serial correlation. Okay, the error terms are serially correlated. Okay, if that were so, then best I go for a log linear trend model, log linear model. Okay, good. Everyone comfortable thus far? No, I hope I haven't told you anything new just yet. Nothing overly new. Okay. Top of page 6, guys, limitations of trend models. What are some of my limitations? Okay. One of the limitations, and again, this is not new, it's called serial correlation. We saw this last week when the residual terms are correlated with each other. And where's that most prevalent, guys, and what kind of a series? Time series. Why is it so prevalent in time series that you're going to have the residual terms being correlated with each other? Because in time series, what happens today is quite strongly dictated to by what happened yesterday. There is that correlation. Why? Because it is time-based. That makes sense, guys. Okay. Don't look at the notes. Okay. How do we test for serial correlation? What do we use? The DW, the Durbin-Watson approach. Remember the Durbin-Watson approach? And what did we say? There he is again. DW is equal to, and guys, this is a vital one that you remember. We saw this last week, but just a bit of revision. It's 2 times 1 minus the correlation coefficient. Okay. Good. Okay. And remember, when we looked up, and don't spend a lot of time on this, guys, but when we looked at the Durbin-Watson details, or the table, the Durbin-Watson table, there's always going to be a upper and a lower level. Remember, guys, there's the Durbin-Watson upper and the Durbin-Watson lower. So it's the other way around, Durbin-Watson lower and upper. And within this range, it's a little bit of an uncertain range. Once you move past there, you can have a much more certain answer. We'll have a look at that in a second. Okay, good. And remember this, guys. This is the key to the whole answer, by the way. In the event that the Durbin-Watson is less than 2 and starting to near to 0, it's positive serial correlation. Okay, what's positive serial correlation? Moves in one direction. What did our picture look like? Like that. Or could be like that. But once it's moving up, it goes up, 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 up till it turns down. Then it keeps moving in that direction. Negative serial correlation does that a little bit, doesn't it? There's no clear picture. It could be doing anything. If it goes up one day, it'll go down the next day. It goes up, it doesn't go up, 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 or down, 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 down. It's a negative serial correlation. Okay, and that's obviously when do you get negative serial correlation as you start to near 4, greater than 2. Okay, there we go. Everyone comfortable with that? But we've seen this all. This is just purely a revision from last week. Okay. Let's start the next one. Learning outcome statement 6C. One of the key features of a log linear model of a time series is that the current period values are related to the previous period values. We call that auto-regression. So an AR model is what we're going to use, guys, when we want to depict this relationship, that this period's results are linked to last period results. Look at my equation. X is equal to, am I boring you yet, B0, which is your intercept, plus, look what's changed now. Okay. Now, Because look what I'm trying to predict. If I just take you back to the beginning, I'm trying to predict x t, the value of whatever the x is, but when? Now. T is now. And how do I get to what the value is now? The value of whatever x is now is equal to an intercept. You happy with that? As there always is. Plus a slope times by what? What x was last period. T minus 1. You happy with that? Okay, so as soon as I'm working with an AR model, an auto-regressive model, I'm just regressing one period over the previous period. Why am I doing that? Because there's a definite relationship between this period xt and xt minus 1. Okay, you happy with that? And what if there was 2 periods? Wow, that's a huge change. I go from AR to AR2. Why? Because I'm regressing 2 periods. And an AR3 model, sure, very fancy. That's 3 periods back. In other words, what am I saying? And let's just try and get the concept right, guys. If I use this model and I say xt, now you've got to understand this. Xt is that thanks, guys. For some reason or other, unbeknownst to me, which is much more complicated than this, is the printer printed 5, 4, 5, 7, 8, 9. That I can never explain to you or to help you understand. This I've got a chance with. Anyway, so we have printed you number 6 over there. Please just grab one. Those are the CFA questions that you guys would be missing in your files. And I'm always impressed when you tell me it's missing in your files, because then I know you've gone through your files, or that you're busy with your files. Okay. Look at this one. If I'm using an AR1 model, guys, tell me what I'm doing over here. So let's go. There's AR, and they don't call it an AR1, it's just an AR, an autoregressive. And an AR model says what? XT is how do I determine the value of X now? What's it dependent on? It's dependent on normal BO plus what? B1. When? Okay, X last period. You happy with that? And I can explain away what? I can explain today's results, XT, by using what? Just yesterday's. You happy with that? Almost all of the variation in today's results can be explained by using yesterday's. There's a huge amount. What would you say to me? That there's a huge amount of explainability, or that the coefficients are what? Significant. What if they weren't so significant? And I looked at the thing and I ran I'll show you in an over table now, and it wasn't so significant. Then you know what I do, guys? I run back to an AR2 model. What's an AR2 model? I don't just use yesterday's results. What I also use, so if I so that it's explained by what? Yesterday's results. So those will all come down, but plus what also? B, X, T. I go back 2 days now, and maybe if I use yesterday's and the day before that, maybe that'll help explain it a bit better. And if that doesn't work, maybe let's try use 3 days, AR3 model. You see what I'm doing? It's exactly the same thing in essence as doing what, guys? Is if I'm trying to explain grades, which is what? Your X, so your Y variable, remember? And if I only use one X, for example, hours studied, I may not get such a huge amount of explainability. What would I do? Let's add another one. Amount of sleep, amount of classes come to, etc. You see what I'm doing over here? That's all the AR does. I'm sorry to disappoint you. Correct. Brilliant. And it's a nice way of understanding it, but really, all it's really saying is that I can explain today by yesterday. You happy with that? Okay. And the best way, let's have a look at an example. Just before we look at an example, sorry. Okay. This is what upsets everyone, but it's actually not so upsetting, to be honest. One of the key assumptions to be able to use an AR model, and it makes sense, guys, one of the key assumptions before I can use an AR model, what is an AR model? It's a model that does what? That explains today's data by using yesterday's data. You happy with that? Okay. Is that it's got, and this is the key word almost for this chapter, almost the key word, that the data has got to be what? Covariant stationary. And look, let's break the words down. Stationary means standing still. Covariance. What are my three key things, guys, when I look at some of the numbers? In order to get to covariance, what would I need? I would need mean. There's my mean. You're happy that expected value is the same thing as mean? Expected value is also equal to mean. You're happy? Variance and covariance. So those three things are what? Are constant and finite for all periods. Constant and finite. Constant and finite. So what do we say, guys? In order for something to be able to use the AR model, which is a time series model, what does things have to be, guys? They've got to be covariant stationary. In other words, that all the parts of covariance, mean, variance, and covariance have all got to be constant and finite across the period. No changes. Remember, as it starts to change, remember, if it changes, then what? It's not going to help me explain today. Well, I can't use yesterday's to explain today if it keeps changing, can I? AR says I can use yesterday's to explain today, but what's got to be? The numbers have got to keep the same. It's got to be covariant stationary. The variance doesn't move around. The mean doesn't move around. And the covariance, the interactions between the two don't move around either. Because if they did, they would be called, give me it's a fancy term, guys. Then they're called not covariant stationary. Well, and if they're not covariant stationary, then I can't use AR models. It becomes a problem. Okay. Yeah, we're still going to test for that. Don't worry. Remember the unit root? He's coming back. We'll look at the unit root in a second. Okay. Let's go. An AR2 model, guys, I've shown you this already. I'm not going to spend too much time on this one. Okay, look at this one. What's changed? I've just added in, instead of just using a B1, I've now added in this one, which is B2 X T minus 2. What am I doing? I'm going back 2 periods. And if I wanted to, I could add it to an AR3 model. Okay, good. There's a third model. There's AR1, AR2, and ARP. What's ARP? It's periods. So it's not a new model, is it? You can just put however many P's you want. If you wanted it to be a 3-period model, then your P will become a 3, won't it? That's all. Okay. Good. Let's just have a quick look over here. Okay. Now I'm looking at it slightly from, instead of using it as a, trying to say, well, here's my XT, and I can predict XT from what happened in the past. The question is, can I now use this to forecast? That's what we can look at here. Forecasting with this model. And if I'm looking to forecast, then what am I going to say? I want to say that X T plus 1, and what's that now? That is next period is equal to what? Intercept plus what happened last period. You happy with that? That's just looking at it from a different point of view. What are we saying again? I need covariant stationarity. I need to make sure that the periods are linked to each other. I'm just looking from the other point of view now. You happy with that? That's all. Okay. Absolutely. That's the last part of the class when we look at things like, is the model properly specified? Maybe we need to make changes over here. We're at this point, Graham's right, but at this point we're looking at a perfect world. Okay, good. And once I've got, guys, once I've calculated X t plus 1, what can I then now I've got xt plus 1, haven't I? This is a little bit like bootstrapping. Now that I've got xt plus 1, what can I calculate? Xt plus 2. And once I've got xt plus 2, I can work out what will be in the third period. Let's have a look. Okay. Just a nice, simple, easy example, guys. It's nothing too crazy. Assume that the current value of x is 10. Okay. Okay. And there's my numbers. Current value, and I got this from the regression equation over there. Okay. What if I wanted to calculate now? So now I've got x. You happy with that? I've got xt. I know what it is. What is it? It's equal to 10. How did I get to 10? I used that equation. Correct. Okay. Well, I had sales of 10, or I had whatever it happens to be. Whatever is time time sensitive. Okay. What's the so xt? Everyone happy? Xt is equal to 10. The formula for the 1 period ahead forecast is it's going to be equal to x. Xt plus 1 is equal to bo. You happy? The intercept plus b1 times xt. Now it's just a plug and play, isn't it? We know what b0 is equal to from that equation. It's equal to 2. I got that from here. Okay. We know that b1, okay, the intercept, the slope, sorry, is equal to 0.6. I got that from here. And what was t? Equal to 10, wasn't it? I've already calculated that. Therefore, t plus 1 is equal to 8. You happy with that? That's just writing the regression slightly in a different way. What would you tell me now if I had to say to you, just in terms of the explainability of it, guys, if I had to say to you, t was equal to 10, t plus 1 is equal to 8. What kind of relationship have I got here? Bit of a negative, haven't I? Keeps going down, whatever it happens to be, and I don't have enough information in the question, but that over time it tends to go down for whatever reason. Okay, and of course it's going to go down because if you look at the regression equation, guys, what is it? That the next day is a fraction, a 0.6 of the previous day. You happy with that? So tomorrow's day is going to be 2 plus 0.6 or 60% of what today's was. You guys comfortable with that? Okay, and guys, of course, then you now that I've got t plus 1, I can go calculate t plus 2, t plus 3, etc., etc. And what do you notice about, I'm not going to do the calc with you guys, what do you notice about t plus 2? What does that come out to be? 6.8. And of course it does, doesn't it? It keeps on going down, and so it will over time. You happy with that? And then I could get, now that I've got t plus 2, I can calculate t plus 3, etc., etc. Okay. Everyone with me? Nice and simple. Okay, nothing too crazy just yet. So what have we seen? We've seen linear trend models, log linear trend models, and now we've seen AR auto-regressive models, which are purely, that today's result is purely linked to yesterday's on an AR1 and AR2. I take 2 days back, AR3, etc., etc. Does that make sense, guys? Okay. Sure, you should be able to, yeah. No reason why not. Good question. Okay. And now, purely revision. 6E, autocorrelations. We've seen these before. Serial correlation, which is also called autocorrelation, is a violation of one of my rules for what? For multiple regression, or any regression. Okay. Remember, guys, I'm not spending too much time over here. We had positive serial correlation. How would you know, by the way, guys? Okay, I'm pushing it a little bit here. How would you know if you had positive serial correlation. What was your Durbin-Watson score? Less than 2. So generally speaking, positive serial, I'm looking at a if it was perfectly positively correlated, okay, I would have a Durbin-Watson of 0, wouldn't I? Negative serial correlation, I'd have a Durbin-Watson of 4. No correlation, I'd have a Durbin-Watson of 2. Okay, and how did let's just test it quick? What should you let's just test on a let's say, for example, a Durbin-Watson of 4. Remember, Durbin-Watson is equal to 2, 1 minus r. Are you happy with that? Now, if it was perfectly negatively correlated, what would my r be? Minus 1. So let's plug it in. 2, 1 minus 1. You happy? Is equal to 2 times 2 is equal to? You happy? Let's go the other side, guys. Just quick. Just because this is so important, guys. Durbin-Watson 2, 1 minus r. And if it was perfectly positively correlated, it would be 2, 1 minus. And if it's perfectly positive, what's my correlation? 1. What's 1 minus 1? Good. What's 2 times 0? 0. Okay, you guys, are you comfortable while I've given you these two numbers over here, guys? Durbin-Watson of 0, perfectly positive correlation, and negative. Okay. What did we say when we had autocorrelation? Either perfectly positive or perfectly negative or somewhere in between. The standard errors become unreliable. Okay. And if the standard errors are unreliable, then what? It's very difficult to test my coefficients, isn't it? Because how do I test my coefficients? I take my coefficient divided by my standard error and I get to a t-stat, don't I? Now, if the standard error, which is exactly the one that's in the middle, is unreliable, I've got problems in my testing, don't I? Okay. Good. And here's the key, guys. To the extent that autocorrelation is an issue, the AR model might not be the best, is not the best model to use. Okay. Now, the following steps can be used a little bit for you, Graham, if the model has been correctly specified. So start off, guys, and we start off the very first step is I'm going to use an AR normal model. Normal model is that my xt, my time period now, is determined by what? Intercept, slope, and last period. You happy with that? Okay, that's a 1 period back model. Okay, then what I do, step number 2, is calculate the autocorrelation of the residual terms. Okay. And how would I know if there's any kind of autocorrelation, guys? I'm testing if the correlations are, what would I want? I want them to be equal to 0, don't I? Because if they're equal to 0, then there's what? No correlation. Good. Okay. Let's have a look. You've seen this example. That's your standard error. We saw that before. 1 over the root of t. That's your standard error, etc., etc. Let's have a look now. Okay. Remember, all of these calcs, guys, are most likely going to be given to you in the exam, but we know how to calculate them anyway, don't we? The t-stat, which is normally the third column, is equal to what? Your regression over your standard error, or your correlation over the standard error. Let's go. Okay, an analyst is looking at a model to predict future inflation rates. The data used is CPI over the last 360 months. He starts off with an AR1 model. Okay, let's go. Look at my AR1 model, guys. Okay, nothing there that you haven't seen, am I right? It's probably starting to bore you a little bit, but let's rather be bored than unbored. You've seen this how many times before? Okay, coefficients we know, don't we? Standard errors we know. The t statistic is what? It's coefficient over standard error, am I right? Okay. R squared, you guys, do you know what R squared is? Okay. Could you work out, let me just make you mad for 1 second, could you work out the correlation coefficient? What's the correlation coefficient? Square root, brilliant. So from that, I'm just on my calculator for you now, guys, is 45. So your R, or your correlation, is 0.45. Okay. Your coefficient, yeah, that's your R squared, that's your coefficient determination, same thing. Okay. There's your standard error, etc., etc. Observations we've got. Durbin-Watson of 1.8. What are you guys leaning towards with the Durbin-Watson of 1.8? That's close to what? Closer to 2, isn't it? And closer to 2, what would you tell me? Have I got an issue or no issue of autocorrelation? Shouldn't be, am I right? Shouldn't be. Just looking at the, I haven't tested we'll test the autocorrelations now, guys, but at this point, it doesn't look like there's too much of an issue, just on pure observation. If that was a 2, then I would say for sure, am I right? There's no issues over here, because the Durbin-Watson of 2 means what? 2, 1 minus, and if there's zero correlation, what's your correlation coefficient? 0, which is what I want, don't I? And 2 times 1 is 2. So whenever I've got a 2, what can you say? Then there's no correlation. Good. So you can see at 1.82, I'm nearing to 2, so there's not much, shouldn't be much correlation. We never want correlation, because remember, these are the correlation among the error terms. I don't want correlation. Then I've got a problem of autocorrelation, serial correlation. Then it's not so good to use AR models. It's a mess. The standard errors are unreliable, etc., etc. Okay. Now we want to see if the coefficients are statistically significant. We've got 359 observations. You guys happy with that? How many variables, parameters? We've got 2. Okay. I'm not going to bore you with going back to the table and trying to find exactly where we are, because there's no 357, there's no 355, there's no 359 on the table. Remember what we saw last time? It sits in between 100, 200, and then it goes up to the 1,000. Okay. So assuming a level of significance of 5, guys, the critical value is 1.97. And by the way, what do you notice? That's almost carbon copy if I take you back there. Remember that one? Back to the table. We've seen this before. Hasn't even changed. Okay. Going back. Good. Based on this, we can conclude that the coefficients, okay, are statistically significant. Why? Because 6.9 and 9.5 are greater than 1.97. You're happy? So these are statistically the coefficients. The intercept and the inflation rate, the BO and the B1 are statistically. Is everyone happy with that? But now, okay, now I want to see, are the residuals correlated or not? Have I got an issue over here perhaps of auto or serial correlation? Okay. I run my numbers again. We start to look again. And here, by the way, it's interesting. Okay. I compare my 1.97, which is my critical value. You guys comfortable? To absolute values over here. Let's have a look. Okay. Not just to, it doesn't matter minus or pluses over here. I'm comparing 1.97. You can get rid of the minus in it, to absolute values. Okay. Obviously, I would like all of them to be higher than 1.97, wouldn't I? Okay, but what's my problem? Okay. Okay. That there and there. Okay. 1.97 is lower than those two, isn't it? Okay. And I've got a problem of auto, excuse me, of serial correlation, and the model is misspecified. Okay. What's that? We will use absolutes. Yes. Here's, I'm just trying to find that exact word for you. It is somewhere here. La, 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 la. Here we go. Remember that one. All right. Absolute value. Okay. So it's lower than those two absolute values. Okay. And obviously then I got it. Then I conclude what? That it is a problem. Okay. Let's go further, guys. Don't be sorry. What's that? Yep. 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 Okay. Yes. Yeah. Sorry. You're right. And that's how you that's how you get your 0.528. Where there's two variables. Would that change? I don't think so. I think you just use all your observations. I think. I can check that for you. All right. But again, don't stress about those deep calculations. That's not where the 99.9 they're going to give you this data. They want you to interpret it. Happy with that. But let's just I will check that one for you. And I suppose the more variables you add, then probably it would change. I think, yeah. My sense is, yeah. Okay, let's go. Okay, so but is everybody? If I stop at this point, guys, I've got a problem, don't I? I've run my AR1 model, and what have I come out with? That there is a problem of serial autocorrelation. So, what does that tell me? That my model is not correctly specified. And then now what would I do now? Oh, if it's not correctly specified, now I'm going to run to what? AR2 model. Let's add on more and more and more until we get to a correctly specified model. Okay. Okay. Use AR2. You happy with that? Okay. Here's your answer. We now have 358 observations. Okay. With 3 parameters. Okay. 355 degrees of freedom. And what will that change, by the way, when I look at my table? Not much. I'll still get 1.97. Am I right? As my critical value. Over our page. I run all the numbers again, guys. Okay. You happy over here? Is everyone comfortable here where I've got another regression over there? Because what's happened now? I'm trying to explain T not just with last period's numbers, but with 2 period ago's numbers. So that would be last, that's T minus 1, you happy? But I'm also going to be using T minus 2 and my intercept. And I've got how many coefficients? Variables? I've got 3. What difference does it make? Hardly anything. Still want to be 1.97 when I start to go to my T tables. It doesn't really have much of an impact, of course. But of course we get to the right answer, but remember the impact is going to be almost nothing. Okay. They give me my standard errors. There's my T statistics. Okay. Let's go again. And you can see, guys, it can become a little tedious. Okay, but let us carry on. Okay. When I look at my T statistics, what happens now, guys? Tell me if there's anything that you... Okay. Everyone happy why I'm using 1.97? Okay. Based on this, we can conclude that all 3 coefficients are statistically significant. Let's put the 1.97 critical value over there, as their T-stat values differ from 1.97 on either side. Okay, they're all bigger than 1.97 on either side. We reject the null hypothesis that the intercept is equal to 0 and that the coefficients are equal to 0 in favor of the alternative, blah, 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 that the coefficients do not equal 0. We've seen this many, many times before. But but by the way, remember, guys, I got to the same point last time, where I could also, for those 2, I could say that they were statistically significant. But now I've got to test for the auto or residual correlations. Okay. Okay. We run our numbers again. Since the critical value is 1.97, and remember guys, I'm using absolute values, 1.97, and what do we see? 1.97 is greater than all of those. In absolute, if I make all of those absolute values, 1.97 is bigger than everybody, isn't it? Okay, in which case I can conclude that there is no serial correlation, and now the model is correctly specified. It's only correctly specified because I've moved from an AR1 model to an AR2 model. That makes sense. So you may need to keep shifting your model, adding in more and more variables until such time as you can see that the model becomes correctly specified. Okay. No, you can see when I'm calculating here, you don't worry too much about this. I can see it's troubling you, but don't stress too much about that. When I'm working with when I'm testing my regression coefficients, then I always go 358 observations, less 2 or less 3. 2 was in the AR1 model, you happy? 3 was in the AR2 model when I add in another variable. But when I'm testing my serial correlations, then I don't. Remember, there's two tests going on over here. First, I've got to test the statistical significance of the coefficients. You happy with that? That's my first test. What are my coefficients? It'll either be 2. If I take you back over here, there's 2 in an AR1 model. You happy with that? And there are 3 in an AR2 model. AR3 model, there'll be 4, blah, blah, blah. But for the autocorrelations, I'm going to keep with my number of 359. You happy with that? So there's two separate tests that are going on. Does it help you? Okay, good. Everyone comfortable thus far? Okay. I want to do a little bit more, and then we'll take ourselves a short break, and then we will knock it off after that. But is everybody kind of thus far? So if we really had to summarize what we've done up until here, what would you tell me? We've seen linear models, linear trend models, okay, log linear trend models, and then I moved to AR1, AR2 models as well. And what do we say about autoregressive models? We saw two big important things about them. Number one, in order to use AR models, they've got to be what? Covariance, stationary. In other words, the mean, the variance, and the covariance don't change over time. And what else? They cannot be exhibiting serial correlation. So if those two things are in place, then I can start to use a AR model, an autoregressive model. Okay. We look at this next thing. Okay. Okay. We're looking at mean reversion. And you guys, by now, you know about mean reversion. What does mean reversion mean? That everything reverts back to its average level or its mean. Who made this mistake? What's the error with this, by the way? Mean reversion. Ask the guys at long-term capital management. Am I right? LTCM. What went wrong, by the way? Let's say, for example, something normally trades at 100. They were obviously looking at bond spreads, the spreads between two different kinds of bonds. But let's say something trades at 100, and all the time, and now it goes down to 80. What do you expect in terms of mean reversion? It'll go back up to 100. Am I right? It makes sense. Now, I want two things that could go wrong. You know, you said that all those adverts. I don't even know what insurer it's for. They say, like, what could go wrong? Is it Sanlam? Could be. I don't know. What could go wrong here, guys? It's at 80. So if it was so easy, what would you do? You'd work out a way to calculate what is the mean level of every asset on the market, and you run yourself a nice Excel spreadsheet, and all those assets that are trading below the means, you buy. Those that are above the means, you sell. You can make a fortune. You can shop at all the Black Friday sales till you don't even need to go to the Black Friday sales. You'll be so wealthy. Okay. So then what? What could go wrong? Give me two things. Number one, there may well be a structural change. We often call that regime switching. Something's changed inherently in the picture. Okay. And number two is, what's the number two? A big one, which hurts a lot of the markets. It overshoots Okay, I can see your economic roots coming through here. Okay. Okay. What's the other side? That it may well mean revert back to the 100, but what might happen until then? You run out of time, am I right? Or out of liquidity. Because remember, as it goes down, so it goes to 80, then what happens? It may go to 70. Okay. And as it goes from 80 to 70, then what happens, guys? You've got to put down margin calls, don't you? Or pay for something you might run out of time or liquidity, and then what happens as you run out of liquidity, then you got to get out of the position, and the next day it goes back to 100, doesn't it? The big short. Yeah. Okay. Some lovely books. Vert, I'd be reluctant to tell you to read a nice financial type book in the holidays because I want you to be studying, but yeah, that's a good way of relaxing. To take a bit of so you feel like you're still a little bit in the program, am I right? The Big Short's lovely. It depends what you enjoy. There's so many good ones out there. For The Economist, there's a random walk down Wall Street. Famous economist Burton Malkiel wrote that one. Lovely book. If you like quants, if you come out of these 4 or 5 class on quants and you're really feeling sure this quants might be your calling, okay, you can pick up any one of Taleb's books. Nicholas Nassim Taleb, outstanding, a real thinker. A little bit deep sometimes. You've got to really just, yeah, The Black Swan, that was his first one, I think, if memory serves. But he's got a couple. He's got Fooled by Randomness, and there's another two, lovely stuff. But each to those. You can't. When I read The Black Swan, it was my wife's favorite joke. She used to tell everybody that I'm on the same page of The Black Swan for about 6 months now. Because I used to get into bed and I read that page and I'm trying to make sense of it, but I'm tired now. It's late at night, and I fall asleep. And you must look at what my copy of Black Swan looks like, by the way. It's like bent over because I would fall asleep on it and then on the. So, not an easy read. Okay, it's not a smooth, easy read. If you're looking for it's not a beach read, by the way. Yeah, no, but but he's a very clever man, and obviously it's a well. Of course, he doesn't need my approbation, but okay, guys, let's look at the mean reverting model. Okay, good. If the time series is at its mean, then the predicted value will equal the current value. Am I right? It's at its mean already. So what will it go to next period, guys? It's there already, isn't it? It's not going to move. Okay. Good. Look at your mean reversion. Don't worry too much about the understanding of it. This is what I want you to get. This is your mean reversion equation. What's your mean reversion equation? You know all the terms over here. B0 is your intercept. 1 minus your slope. Okay. Okay. If it's covariant stationary, guys, and don't get it taken over by the words. If it's covariant stationary, then the mean reverting level is also, it's finite, isn't it? It's not going to move. Why? Because your data is covariance. You guys comfortable with it? We'll discuss it later on again, but okay. Good. Let's look at an example. An analyst is looking at a model to predict future companies' gross margin. Quarterly data is used. 60 months are used. He starts off with an AR1 model. And guys, obviously, if you were in practice, my advice to you always would be start off with an AR1 model. That might be enough in terms of its explainability. If that doesn't work, well, you'll keep specifying until you get what you need. Let's go. Am I boring you yet with these tables? I hope I am, because by the time the exam comes, I want you to, one of these again. Can't they do better with their question? Is this all that they got for me? Okay. The table below is an extract of the regression results. And by now, guys, you know, how do I calculate my t-stat? My t-stat is just going to be my coefficient divided by my standard error is equal to my t-stat. But obviously, as I said to you guys before, they generally give you the t-stat. They give you all the numbers as well. You happy? Let's go. There's my regression equation. Nothing too crazy over there. You've seen this about a zillion times, haven't you? Okay, nothing I can add too much value over there. And you're going to run xt. How do you get xt? Xt is the value now. Remember, it's t. How do I get to t? I use t minus 1, don't I? You guys happy with all of the equation, all the numbers over there? And I get to 66.37%. You guys comfortable? Okay. What I do, what is that? That's the level where it is now. You happy with that? It's sitting at 66.37. Now, what I want to do, I want to calculate. So that's where it is now. That's its current value, the predicted value for its now. Okay. And what I say, okay, I go and run myself a mean reverting equation. It's this one over here. Very, 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 very important equation, guys. I run that equation, and look what I get to. Okay, that according to my prediction, it's going to be 66.37. That's per my prediction, per me running a what? A regression model. When I then go and look at a mean reverting model, what does it tell me? Oh, no, it should be at 70.36. What does that mean? Okay, that anything below 70.37, if that is the level, what's going to happen? It's going to rise up to get to that level. Because it's currently, my predicted level is lower, but according to the mean reversion, okay, it should rise up. Correct. But and Graham, that's always going to be the issue, isn't it? When exactly will it mean revert? But the current mean reverting level, if I had all the data, would be what? 70.36. That's the mean. Why is it not there now? Well, I can't tell you that. Why is anything not exactly where it needs to be right now? We don't know. But what I do know is that it's going to get to that level. It should get to that level. Okay. Well, remember, like in gross margin, not really. But remember, if I'm looking at a stock and I see that the average return over the last year is sitting at 66, and perhaps that's what the market's pricing in, that this share will do 66% in terms of its margins, gross margins in terms of its results. But I know really that it's going to get higher. It should be at the 70% level, which means that what? That the results are only going to get better and better. Am I right? Might be a good time to get in. Do you see what I'm saying? Okay. Good. Last little bit, guys, we'll take ourselves a break. Comparing forecast model performance, guys, very important. There's a massive difference between in-sample forecasting, guys. This is the basis for what we're going to see next week, which is machine learning. It's very nice to teach your machine how to learn. Okay, if you're going to only teach him based on what? In-sample. You say to your machine, look, here's a nice sample of stuff, and what does he do? He learns from that sample. And what comes out? This is a very clever machine. But what can the machine only work with? That particular set of data. When I now move to out of sample, and I say to him, do me a favor now, I want you to predict what will happen with other data, what does he say? He's not so accurate anymore. You've only taught him on in-sample. So in order to make something a much more robust or a better learning machine, what must you teach him? How to learn on both. In-sample, that you would have to have good results or low forecast errors in sample and out of sample. If you've only got good results for in-sample, then I'm not interested in your model, because your model will only be able to predict on the data that you've given it. And that's very nice, but it's limited, of course. Okay. Good. Just a quick look over there, guys. By way of the way to compare out of sample is to compare the root, the RMSE. Okay. And we saw this before, didn't we? There's nothing new over here. Okay. The smaller the RMSE, the more accurate the model, the more explainable the model is. Where was RMSE? That's just the means, am I right? That was the very last column of what we saw in the ANOVA table previously. Look over here. Let's just have a quick look at an example, and then we will take ourselves a break. Okay. Assume that we had 50 actual observations upon which we built our model based on that. So we built ourselves a nice predictive model based on 50 actual observations. An example of out of sample areas would be to only use the first 30 observations to, so let's say for example I do have 50 actual observations. Okay, what would I do? The best way to try and get my model as accurate as possible, if I've got 50 observations, what would I do? Use 30 observations to derive your model. In other words, what do I mean? What do we derive the model? Come up with my prediction, come up with my regression equation, come up with my ability to predict based on only how many? 30. Then what would I do? And that would be called what? In sample data. I'm using the actual samples. Okay. Well, you can pick any 30. Probably random is the best way, isn't it? Always going to be more accurate if you do it randomly as opposed to selecting the exact ones that you want. Then you, okay. Then use the predictive model to predict what the results of the next 20 would be. You've got them already, don't you? But use your model to predict them, and then you can do a comparison to see how accurate they are. Okay, good. You guys comfortable with that? Just two different kinds of models. Very important that we understand the difference between those two. Guys, it is now just before 7:30. Okay, go grab yourself something to eat, to drink. I'm going to start again, hopefully about 7:45. You've got about 15, 20 minutes. If your food's not ready, bring it back. Okay, see you guys now.